conference underway. And this is a talk that I've been looking forward to because it's an interesting connection between graphs and groups that I had not heard of before I read this abstract. So can we please welcome Yuming Jiao from University of Technology, Sydney.
Yeah, thanks, Gordon. Thanks a lot for your interest, and I hope I won't disappoint you. So so this is some, as the title reflects, this is some new connections between groups and graphs that I've recently found with my collaborators. Here are my collaborators Yina Li, Xiaohui Bei, Shiteng Chen, Qi Guan, Xiaoming Sun, and Xiaoyu He. So yeah, basically we found this connection in 3 papers, but basically based on the same construction of groups from graph. So I guess this is the first thing I need to talk about. So there's a interesting connection construction. Basically it goes from graphs to bilinear maps to groups as follows. Before that, let me just say that for this talk, we just consider simple and non-directed graph on vertex set being the square root bracket n, which is just the number from 1 to n. And we also fix an odd prime p through the talk. So this procedure is what we call the Beer-Lovász-Tott procedure. So as you can see, it starts from a graph, then you construct a bilinear map Fg, and then you construct a P group PG. So a little bit more detail is the following. So let's start with such a graph G. And now we can construct an alternating bilinear map Fg. Here alternating just means that for any vector u, we have f. When we apply f to u and u, it's just 0. So this is alternating. And then from this alternating bilinear map Fg, we can construct a P group of class 2 and exponent PG. And class 2 basically means that the commutator subgroup is contained in the center. And the exponent P means that for any group element, G raised to the P power is the identity. This is kind of has been investigated by previous works. For example, by Mackler in the 1981, and more recently by Rossmann and Ball in some other contexts. So this is not really a new kind of like folklore, I guess. So let me describe this construction in more detail. And but basically this relies on the so-called elementary alternating matrices, which is a simple notion. I guess most of you come across this from time to time, but this is also to kind of fix some notation. So as before, we use a square bracket n to denote the integers from 1 to n. And we also, for example, let ij be a size 2 subset of n. And we use ei to denote the I standard basis vector in f to the n. And then the elementary alternating matrix, aij is just ei ej transpose minus ej ei transpose, which is pretty simple. Basically, the ij position of aij is 1, the ji position of aij is -1, and the other entries are 0. So here is a simple example, which illustrating a through 3 with n being 4. So this is just a simple demonstration, and we are going to use this in the construction. So yes. Good, now I can use laser pen just as in class. So the first step, let's construct a bilinear map from a graph. So let G be a graph, graph G on the vertex set being n. And let's assume that we have m edges, and we write it explicitly as a set of size 2 subset, I1, J1 up to IMJM. And for any k in M, we let AK to be the elementary alternating matrix corresponding to the kth edge, namely just the edge with vertices being IK and JK. And now we can construct a matrix tuple, A1 to AM, and by this tuple, basically we mean that put some arbitrary order on the edges, but this is not so important. And from this matrix tuple, of course, because all the AI, now they are alternating matrices. So we can construct an alternating bilinear map Fg. using these matrices, these M matrices A1 to M by the following. Namely, when you evaluate Fg on U and V, basically you just do U transpose A1V up to U transpose AMV. This is a row of numbers. You take the transpose, you get a vector, because we are going to use column vector throughout the talk. So this is a construction from graphs to bilinear map. And this is basically traced back to the work of Tuta and Lovász. Now, we are going to do the second step, namely from a bilinear map, we are going to construct a group. And this is the construction goes to Bayer in the 1930s. So let F be an alternating bilinear map over Fp, and P is an alt prime. And we can construct a P group of class 2 and call them PPF by the following. First, the set of group elements is just the Cartesian product of Fp to the n cross Fp to the m. So the group order is basically P to the n plus m. And the group operation is as follows. So suppose you have V1, U1, and V2, U2. You basically do the following. For the first coordinate, you just plus, you have V1 plus V2. For the second coordinate, you have U1 plus U2, but now you apply this alternating bilinear map, F applied to V1 and V2 and divided by 2. So this division by 2 is basically why we assume that P is like a 2. So, okay, so this is a pretty classical construction. You can verify that it's, this construction satisfies the group law and it gives you a P group of class 2 and exponent P. And now we, after these two steps, we see how to construct a graph G, start from a graph G, constructed by alternating bilinear map Fg, and then goes get a P group PG. Okay, so this is a pretty classical construction, and let's see what this construction will bring some surprises. So, yeah, so we are going to talk about the following properties, graph theoretic properties and group theoretic properties in the following. So the first correspondence is basically a pretty basic. That is the connectivity on the graph side and the central decomposition on the group side. And then the second correspondence will be the maximum independent set size on the graph side and the maximum abelian group subgroup order on the group side. Finally, we are going to talk about isomorphism. Of course, for graphs, we talk about isomorphism as graphs, and for groups, we talk about isomorphism as groups. And our results basically relate the graph theoretic properties of G with the corresponding group theoretic properties of PG. Okay, so the first result is as follows. I will explain these notions, but I guess this is kind of too basic. I guess just explaining the notions makes the correspondence make them look more interesting, so I just explain them. So we say that a graph G is disconnected if there exist at least two connected components. For example, in this graph G, we delete it after deleting this edge, then we get two disconnected components, two connected components. And so this is a pretty intuitive notion. On the other side, we see that a group P meets the central decomposition if there exist two subgroups J and K, such that firstly, every element in little j in J and little k in K, we have they commute, JK equals KJ for every little j in big J and every little k in big K. And second, the P is generated by J and K. And the third, we impose that J and K are non-trivial, they're not the identity group. So that's the central decomposition notion. And not surprisingly, our first result will be to say that P is disconnected if and only if PG admits the central decomposition as such. So this is the first result. And the second result will be talk about the maximum independent set size of G. So it's in graph theory, it's denoted by alpha G. And basically an independent set is just a set of vertices where there are no edge between any two of them. And you can see that the blue vertices here, they form an independent set of size 3, and this is And for this graph, alpha G equals 3. And on the other hand, we talk about basic abelian subgroups, and the large abelian subgroups or P groups have been studied since, for example, April in the 1965. And the second result will be as follows. Suppose our graph G has m edges. Then alpha G equals S if and only if the maximum order of abelian subgroups of PG is P to the m plus S. This m is this number of edges, and this S is basically this alpha G. So that's the second correspondence. Finally, let's talk about the isomorphism. I believe that you all know these notions pretty well, but two graphs are isomorphic if there exists a bijection between the vertex sets that preserve the edge relation. For example, these two graphs are isomorphic. You can verify by, for example, mapping according to the color, right? 1 to A, 3 to C, and you will see that there's an edge between 1 and 2, and there's an edge between A and C. So this is, you know, pretty well. And you know probably even better, I don't know. So two groups are isomorphic if there exists a bijection between group elements that preserve the group operation. And for example, phi is isomorphism basically means that phi applies to G times H in one group equals phi G times phi H, but this multiplication in the second group. So there's two groups being isomorphic. And now we can, the third result says that the two graphs G and H are isomorphic if and only if the two groups PG and PH are isomorphic. So this is the third result. So basically for all the three cases, we get pretty tight connection. Okay, so you may wonder a little bit what makes happen for these proofs. And we will give a peek into one proof. As you can see, this proof is actually not difficult. Let's look at this one. So namely, a graph, suppose we have a graph G with m edges, then alpha G, the maximum independent set size is S if and only if the maximum order of abelian subgroups of PG is P to the m plus S. Okay, so we talk about this construction, right? So this is from G to FG and then to PG. So not surprisingly, a key to prove this theorem is to utilize the intermediate object FG, this bilinear map. And in fact, we are going to talk about this object, namely independent set of G on the leftmost side, and the abelian subgroups of PG on the rightmost side. And what serves as a bridge is the so-called totally isotropic space of FG. Okay, so let's talk about the connection between bilinear maps and groups for now. So let's define, and we'll define what is a totally isotropic space. A bilinear, let F be an alternating bilinear map. Then we say that a subspace U is a totally isotropic space of F if for any U and U prime in this subspace, we have F, U prime is 0. Okay, so basically when you restrict your bilinear map to this U, you get the 0 map. And this is a pretty easy fact and known, I guess, at least since April, and even probably even older. So total isotropic space of F of dimension S, basically they correspond to abelian subgroups of PF of order P to the m plus F. Okay, so this gives a pretty tight correspondence between the dimension of total isotropic space and the order of abelian subgroups. So that's the first connection. This is just quite classical. Total isotropic spaces and abelian subgroups. The other side is a little bit trickier, but still not too difficult. So we want to talk about the relation between independent sets and total isotropic spaces. And it's not difficult to observe that if you have a size S independent set of G, then it gives a dimension S totally isotropic space of FG. So one direction is easy, from independent set to total isotropic space. A little bit trickier is the reverse direction. Namely, suppose we have a dimension S total isotropic space for Fg. How can we construct or how can we get a size S independent set in G? We'll go through this proof because it's really just simple. So let's assume that U is a dimension S totally isotropic space of Fg. And we write a matrix T, which has n by F matrix, whose column than U. So this is just to get it more concrete. And for convenience, we can suppose that the first, because the dimension, the rank of T is X, so we can, for convenience, let's suppose the first X rows of T are linearly independent. We can just say any sub. So in general, we say that there exists X rows that are linearly independent, but it will complicate the notation. So let's assume that the first X rows of T are linearly independent. And now we can claim that actually the vertices from 1 to S, they form an independent set in G. And this is our claim. The first S vertices form an independent set in G. And to prove by contradiction, if not, suppose there exists an edge ij in E, such that actually contradicting that the first S vertices form an independent set. Now we just because remember we use the construction of our elementary alternating matrices. So this ER EJ transpose minus EJ ER transpose will be one of the matrices used to construct Fg. And you just examine the T transpose and T times this alternating matrix, elementary alternating matrix. Then we will say that it's not the zero matrix because the rho and the rho J of T are linearly independent. So, but we at the very beginning we assume that this T, the vector space U represented by the columns of T is an isotropic space. Then we get a contradiction. So you can say it's actually it's a pretty simple proof. And, but this basically gives you the proposition that G has a size as independent set if and only if Fg admits a dimension as totally isotropic space. So to summarize, we just show how to prove this theorem between the connection between alpha G and the maximum order of abelian subgroups of Pg. And this is achieved by using the intermediate object Fg and the total isotropic space itself. Okay, so I guess this is neat, but so the above strategy, they can be applied to the relation between connectivity and central decomposition. But the isomorphism theorem is more involved. Just using that type of strategy would not work. And we have some generalizations. For example, the parametric number of G, which is here I just view parametric number as the minimum D such that you can partition your vertex set into D independent sets. And the so-called totally isotropic decomposition number, which is the minimum D such that you can have a direct sum of D subspaces, and each subspace is the total isotropic space of Fg. This you have a tight correspondence here. And another generalization will be the vertex and edge connectivity of G versus certain parameters regarding the social or central decompositions of Pg. So this is to describe that would require more ink. So let me just mention one example, namely this edge connectivity. So let P be a P group of class 2 and exponent P, and we define lambda P to be the smallest integer S, such that there exists a central subgroup N of order P to the S, such that P, the quotient group P over N admits a central decomposition. So basically you want to find a smallest order central subgroup such that this quotient admits a central decomposition. And here is, on the graph side, this parameter lambda G is quite classical. Lambda G is the smallest number of edges of G such that if you remove these edges, you will get a disconnected graph. This is called the edge connectivity. And here we have the theorem that lambda G equals lambda PG. So that's also a little bit surprising, I think. And its proof while still using FG will be more involved. Okay, so having seen these connections, I guess now we want to understand, okay, what this connection will give us, right? We probably won't be satisfied if we have a bunch of equalities or connections. And I think one interesting thing is that these connections will inspire new questions for groups inspired by graphs. For example, here is a pretty classical question asked by Erdős and Moser in the 1960s. So let G be a graph of order n. What is the largest number of maximal independent sets that G can have? And this was subsequently solved by Moore and Moser in 1965. They show that the largest number of maximal independent sets of G is at most 3 to the n over 3. And this is tight because it's achieved by the graph that consists of disjoint copies of triangles. And now we have the correspondence between independent sets and abelian subgroups. We can ask, so suppose we have a P group of class 2 and exponent P, whose commutator quotient is isomorphic to Zp to the n. What is the largest number of maximal abelian subgroups can P have? Because having this correspondence, you can translate your questions from graphs to P groups in general. And you can see that this question is entirely modeled after the Erdős and Moser question. And we can prove that the number is at most P to the 1 over 6 n squared, but we don't know whether this is tight. The trivial bound will be P to the 1 over 4 n squared, basically the number of subspaces. The number of subspaces of the vector space Fp to the n. And another interesting aspect of this theorem is that it's inspired by David Wood's proof of the Moore-Moser result. So we use some strategy there, but afterwards it becomes more complicated. Still, it gives us some improvement from the trivial case. And there's an example with P to the 1 over 8 n squared maximal abelian subgroups. So the gap between 1 over 6 and 1 over 8 is pretty interesting, I think. Okay, so basically this is a reference. And to summarize, we have seen that the Beer-Lovász-Tooth procedure gives a P group PG from a graph G. And we have seen the correspondences of the structures of G and E of PG. And the intermediate object, which is alternating bilinear maps, plays a crucial role. And finally, we have more recent work on the extremal probabilistic enumeration studies of alternating bilinear maps as follows. So yeah, that's all. I guess I run out the time for, I don't know, 10 minutes. Sorry about that.